Welcome everyone. Today we're going to talk about coterminal and related angles. We're going to start with a warm-up from the second lesson, and I'm going to ask you to pause the video and try this out, and then we'll take it up together. So now that you've tried the video on your own, we're going to start by finding a related angle or a buddy angle of 210. So we can find this by doing 210 subtract 180, and that gives us 30 degrees. Now, the second part of this asks us to find the exact value of 210. So what we're going to do, or sine of 210, I should say. So what we're going to do is we're going to plot 210 approximately where it should fall. And we found the reference angle between 180 and the 210 line to be 30 degrees. Now you're going to complete the right angle triangle with keeping in mind that 30 is your reference angle. And always across from 30, we want to make sure that side is labeled 1. Across from 60 should be root 3. And the hypotenuse of this triangle should be 2. Label your sides based on this reference angle here. So this is adjacent, opposite, and hypotenuse. So this should be equal to sine of the reference angle, and then we need to decide whether this will be positive or negative based on the cast rule. So drawing cast, starting in the bottom right quadrant or the fourth quadrant, we see that we're in the tan quadrant. Now, if I'm taking the sine of an angle in the tan quadrant, I know that my answer will be negative. So negative sine of 30 using SOHCAHTOA, sine is opposite over hypotenuse. We should get negative 1 over 2 as our answer. Okay, so I touched on this in yesterday's lesson, but I told you guys to kind of imagine points on the outside of a circle. So if we think about a circle here, this is going to be a bad circle, I can just feel it. Let's think about a circle. So we talked about this point that can rotate really anywhere on the outside of this circle. There are infinite amounts of points that can be here. But let's just use one in the upper right-hand quadrant as a sample to start. Oh, I accidentally erased my circle. Let's redraw that here. Okay, so I have a point xy. In order to get to that point, I've gone x units over and y units up. And of course, the horizontal and the vertical make an angle of 90 degrees. If I start at the origin and I measure out to that point, this is also the radius of my circle. And we know based on our information, if this is the initial arm and I've rotated out to some value here, that this is theta. So if this is x and this is y, and we have a theta, that makes this adjacent, opposite, and hypotenuse. So if I'm interested in using SOHCAHTOA to set up my trig ratios in terms of a specific point x, y, and the radius of my circle, I can set them up as follows. Sine of theta is equal to opposite over hypotenuse, or in this case, y over r. Cos of theta is equal to adjacent over hypotenuse, or with our labels, x over r. And tan of theta is equal to opposite over adjacent, or in this case, x over y. I also know, because this is a right angle triangle, that Pythagorean theorem stands, which means x squared plus y squared should be equal to r squared. Okay, you can box this up because we're going to use this in this unit. So just highlight it or box it up. Make sure that it's available in your notes if you need to look back at it. Okay, so we're going to use this idea here. So yesterday we went from angles to the ratio. Today we're going to think about ratios and how we can get angles or set up exact values of cos and tan without necessarily even needing to find the angle. So given that sine of theta equals 3 over 5, or the opposite is 3 and the hypotenuse is 5, and that theta lies in quadrant 1, determine the exact values for cosine and tangent. So let's draw a picture. Remember, these are the quadrants, 1, 2, 3, 4. So if I'm in quadrant 1, I'm in this first upper right-hand quadrant over here. And we always have an angle that's kind of being measured outward from the origin. So this is some rotation, theta. And I have some point xy. So I've got a couple distances to make this a right angle triangle. I have the horizontal and the vertical distance that was traveled. And we talked about x, y, and r. And remember, above, sine was y over r, or opposite over hypotenuse. So I do know that this equals 3, and this equals 5. X is the question mark that's going to allow me to set up the exact values of sine and cosine. I don't need to get the angle for this. I actually don't even need to solve for the angle at all in this question. I can use Pythagorean theorem, which we said above was x squared plus y squared should equal r squared. So we see here that x equals 4. So I can set up the rest of my trig ratios. Cosine is equal to adjacent over hypotenuse, or x over r, which in this case is 4 over 5. And tan of theta is equal to y over x, or opposite over adjacent, which in this case is 3 over 4. Okay, now the second part of this question asks us to solve for the theta in question 1 between 0 and 360 that could have a sine value that's the same as the sine value in example 1. So this is sine theta was equal to 3 over 5. Now, when we think about the quadrant grid, and when we list out the cast rule, you should notice that there are 2 quadrants where sine of an angle could give us a positive ratio. The first quadrant is the all quadrant, and this would be a quadrant where sine is positive. 3 over 5 is a positive value. And the other quadrant where sine of an angle is positive is in its own quadrant, the sine quadrant. So I actually have 2 angles that could potentially give me a ratio of 3 over 5 where it's positive 3 over 5. So this actually can be produced by 2 different angles. And the angles have the same degree value as far as the reference angle or the acute angle that makes up those angles. So the first thing that I'm going to get is the first rotation. We'll call this theta 1. And I can find this if it's not a 1 root 2 or a root 3 with a 1 or 2. I can find this just by using my calculator. So we know in order to solve for theta, I have to do the sine inverse of 3 over 5. So let's enter this into our calculator. And you should get out 36.869, so on. So let's round this to, just for simplicity's sake, we'll say 37 degrees. So this measurement right here is a rotation from the initial arm 37 degrees. Now theta 2 is really this rotation right here. But the cool thing about this is that the rotation in between here, or the reference angle, is actually the same as the reference angle from theta 1, which is 37. So in order to find the second possible theta that could give us a ratio of 3 over 5 for sine, I can actually calculate this by doing 180 minus the reference angle, which is 37 in this case. and that gives me 143 degrees. So you can actually test this in your calculator. Take the sine of 37, and you should get a decimal that's approximately equal to 3/5. So 3/5 is exactly equal to 0.6. So when you do the sine of 37, you should get something like positive 0.6. You're going to have a little bit of decimals because we rounded that answer. And I also want you to try the sine of 143 in your calculator. So you actually get the same answer. And that's because sine in both of these quadrants has the same reference angle and it produces the same ratio from sine. Find another angle that will have the same cosine value as in example 1. So in example 1, we found that the cos of theta was equal to 4/5. So let's look at our quadrant grid. Four over 5 is a positive value. If it were negative, I would of course see a negative in front of it. So I'm focusing in using the cast rule on quadrants that will give me a cosine of an angle which is positive. So cosine is positive in two quadrants. It's positive in the all quadrant and it's positive in its own quadrant. So I'm going to have some angle here and some angle here where the reference angles are actually equal. So we'll call this one theta 1, and then this rotation out to this angle, this is theta 2. But this little slice inside here is actually going to be equal to the acute angle in quadrant 1, and that's how we'll find the second theta. So if you go in your calculator here and you do the cos inverse of your ratio, you're actually going to get the same angle that we got above, and we'll round that to 37. And this is because this is actually all from the same triangle, right? We produced all of these ratios from this particular triangle in example 1. So we should expect to get the same answer for the first angle that we got from the part A of example 2. Now theta 2 is going to have a reference angle of 37 degrees inside here, but I'm really looking for this exterior rotation, this blue rotation here. So I can find that by doing 360 minus this little 37 degree slice, and that will give me the remaining slice around here. So we should get 323 degrees. Okay, do a little check for yourself. 4 over 5 is equal to 0.8. So does the cosine of 37 and the cosine of 323 give us a value of something close to 0.8? Remember, we did round this, so it's going to be slightly off. But if 4 over 5 is 0.8, cosine of 37 should be very close to that if I found the correct answer. So this is equal to about 0.7986. I think that's pretty close to 0.8. And cos of 323 gives me also a positive value of 0.7986, which I can say is close enough to 0.8. Okay, now if I find the angle in the wrong quadrant, let's say I accidentally did it in sine or tan quadrant, I will get the same value, but I'll get negative. Now I don't want to get negative because I know from up here that my ratio is actually a positive answer. So I want to make sure that my angles fall between 0 and 90 and 270 and 360 to give me positive cosine, positive answers when I take the cos of those angles. Find both theta between 0 and 360, where sine theta equals negative 0.7. Okay, notice I put some emphasis on the negative for that. Okay, sine is equal to a negative value. Now, what does the cast rule tell us? Well, the cast rule tells us that all angles will have a positive sine value here. Sine of angles between 90 and 180 will have a positive value here. But in tan and cosine, it tells me that the sine of those angles will actually be negative. And that's actually what we're looking for. We're looking for the sine of an angle that's going to give us a negative 0.7. So I know that my angle should fall in the tan and cosine quadrant. Okay, and the cool thing about this, again, is that the reference angle between my theta 1 and theta 2 is actually going to be equal for both of these. So there's a couple ways that we can do this. We know we can find sine inverse of the ratio. Oftentimes when it's negative, I find it helpful to find the reference angle by doing sine inverse of the positive version of that angle. But for our sake here, I'm going to do the sine inverse of negative 0.7 so you can see what happens. So we actually get a negative angle out from this. So if we round to the nearest, let's say we'll do the nearest tenth this time, we get negative 44.4 degrees. Now, this is the rotation starting from the initial arm, actually rotating clockwise in this direction. So it's basically just telling us that our reference angle is 44.4 degrees. And here's the key here. We want theta between 0 and 360. Is negative 44.4 in between 0 and 360? It's not. So I actually can't use this as a theta. It is an angle that's rotated clockwise, but I really want the angle in the counterclockwise direction measured from 0 degrees. So theta 2 is actually probably the one that I'll start with because I can find theta 2 by subtracting my angle from 360. So this is how I taught you guys to switch your angle into its positive value, and that actually makes 315.6 degrees. So that's actually telling me this rotation right here. That's 315.6. Now my reference angle really is just 44.4 degrees. So I can also find theta 1, looking for this rotation right here, by doing 180 plus the reference angle, which will give me 180 plus 44.4 degrees. This is 224.4 degrees. Okay, do a check in your calculator. Check the sine of 315.6 and the sine of 224.6, and you should get something very, very close to negative 0.7. Okay, find both theta for tan theta equals 2.1. And I should also mention here that theta needs to be between 0 and 360 degrees. Okay, so if tan equals a positive, let's think about the cast rule. Draw your quadrant grid. Label your cast rule. And you're going to decide where tan will fall if tan is equal to a negative. So where is tan positive? Well, all ratios are positive in the all quadrant, and tan is going to be positive in its own quadrant. So I'm going to have some theta here and another theta here where the reference angles between the horizontal are equal. So let's start by finding theta 1. Theta 1 is going to be found by doing the tan inverse of 2.1. And I'm just going to say we'll round to the nearest whole value here. So let's go 65 degrees. That's this rotation, and this is actually going to be equal here. However, to find theta 2, I want this full rotation. So this full rotation for theta 2 will be 180 plus my reference angle, which is 65. Remember, it always has to be an angle between 0 and 90. That's your reference angle. So we should get approximately 245 for the second angle. Okay, again, do a check of your answer by calculating tan of 65 and tan of 245. It will be off a little bit, but it should be very close to 2.1. Okay, so let's check it in our calculators. Tan of 65 is about 2.144, so that's close enough for me. And tan of 245, this should be giving us out positive answers, is about 2.144 and so on. So that's close enough for me as well. Okay, the more decimals you leave, the more accurate that final check is going to be. Okay, a couple other types of questions that you might see deal with X, Y, and R are questions like number 5. So the point -7, 19 lies on the terminal arm. Find the angle to the terminal arm and find the reference angle. Okay, so if I think about where the point -7 for an X coordinate is and 19 for a Y coordinate is, it's going to go left 7 units and up 19 units on the y-axis. So it's going to be somewhere, let's say up here. There's our point, -7, 19. So in order to get there, we had to go 19 units up for y, and for x, we had to go over -7 units. Now our radius, okay, if we kind of imagine if there's like a circle around here, this is the radius of the circle, so we're going to call this radius. That's a question mark at this point. Now, one thing that you should know is that x, y, these, depending on the quadrant that they're in, can be positive or negative. So we can see here, if I go left on the x-axis, of course my x is negative, and if I go up, then the y is positive. But if I went down from there, then y would also be negative. Now the radius of a circle, because we're talking about the actual kind of length from the origin out to the edge of the circle, radius is always positive when we find it. So here's what I want to know. I want to know the rotation to my terminal arm, which I will call theta. And I also want to know the reference angle, which I'm going to call x. It's actually easier for me to find x first. So if I find x, thinking about this as a right angle triangle, if x is my reference angle, this is adjacent, and this is opposite. So I can use tangent to help me find this. So tangent is opposite over adjacent, or y over x, like we talked about earlier. And I can do the inverse of this to find x. Now remember, your calculator is not as smart as you hope it is. So your calculator just knows that we're taking tan of something, the tan inverse of something, and that the ratio is negative. The ratio can be negative in 2 quadrants, sine and cosine. We know we're in the sine quadrant. Your calculator doesn't, unfortunately. So your calculator just spat out an answer for you of -69.77 degrees. Let's round that, let's say, to -70 degrees, just for simplicity's sake. Okay, well, you know what we do know is that this angle and this angle are equal. So I think we could confidently say that if this is 70 degrees, the rotation doesn't really matter here. If I know that this is 70, then I know that this is 70. Okay, opposite angle theorem. So although we are getting out -70 here, that's basically just telling us we're rotating clockwise. Our calculator isn't as smart as we are, hopefully. So x is 70. Now, here's what else I know. I know that this line is 180 degrees. So I know that the rotation theta that brings me to that terminal arm, or the radius of that circle, is going to be equal to 180 degrees minus the reference angle, which is 70. Okay, that gives me that rotation of 110 degrees. Okay, the last thing that I want to talk about is coterminal angles. So think about the word co. We know some words, we use the word co for a lot of different things. Cooperate, cohabitate. Sure, you can think of others. So cohabitate, we're living in the same house or in the same space. Cooperate, working toward the same goal. We operate together, collectively, together. So think about co as in same. And terminal meaning terminal arm. So coterminal angles are angles that have the terminal arm in the same position. So just so I don't take the example below, so we're talking about 60. So coterminal, if I drew an angle here of 120 degrees, how long would it take me to rotate before that arm was in the same position? So if we imagine this arm rotating around, the arm will fall back into the same position again. If I swing it around, it needs to go a full 360 degrees. So if I start with the angle 120, if I add a full rotation of 360 degrees on that 120, that will actually give me a terminal arm that's in the same location, but I've now rotated it 480 degrees from the initial arm. So the initial rotation was 120, but then to create that angle in the same position, I rotated it another 360 to give me an angle in the same spot, which is 480 degrees. Now I can do this infinitely many times. I can rotate it another 360 after that. And if I do that, I'm going to get another coterminal angle of 120. So that will give me an angle of 840. So all of these have rotations that land us with the exact same terminal arm there. Okay, I can also take my angle here, and instead of rotating it in the positive direction, I can rotate it in the counterclockwise direction. So if I rotate it there, basically what I'm saying is we're starting with 120, and going in the clockwise direction, we know that this is negative 360. So I can find negative angles that are also coterminal angles of 120 by subtracting multiples of 360. So negative 240 is also an angle that falls in this spot. I can subtract 360 again. If I do that, I get another coterminal angle of negative 600. So all of these have an arm that lies in this specific location right here, and that's why they're called coterminal angles. So I want you to see if you can find a couple different coterminal angles for the angle 60. We're looking for 3 others. Potentially, let's say, at least make one positive and one negative. So you can take 60 and you can add any multiple of 360 that you want, or subtract any multiple of 360 that you want. Please make sure you're starting with 60 though. Don't start with 360 and add 60 or subtract 60. This is especially important if you're finding negative angles. So take 60 and add any multiple of 360 that you want. So let's say we add 360 once. We're going to get 420 degrees. This is a possible coterminal angle. If I add 360 to that again, I'm going to get 780. That's another coterminal angle. Let's say we want to find a negative coterminal angle. I'm going to take 60 and subtract 300. This is going to give me, subtract 360. Okay, this is going to give me the angle negative 300, and this is also a possible coterminal angle of 60. Okay, so start with 60 and add 360 or subtract 360 as many times as you want, and you'll get infinitely many coterminal angles.